approximately equal to T in. All right, now to calculate how much the voltage has fallen from here to here, I need to go back to basic circuits and analyze this type of circuit again. So let's go ahead and do that. So let me add a page. Okay, here's the circuit that we analyzed, assuming the diode has turned off. We have a resistor and a capacitor, and we have R1 and C1. There's a voltage, some voltage here. Let's call it V1, the initial voltage. And I would like to analyze the circuit. Now remember from basic circuits that the response looks like this. Okay, so let me call this V out, but I will write initial voltage on C1 is equal to V1. So V out as a function of time for this very simple circuit is like this. It starts at V1, goes to 0, and we know that this equation is V1 exponent minus T over tau. Okay, so that's what we know when a capacitor discharges through a resistor. Now, we are making an assumption that the discharge, the decay, is very slow. Does that allow us to make an approximation for this waveform? Yes, and it's a very good approximation to remember for your career. Oftentimes, it's very helpful. Okay, so let's suppose that we are observing this waveform for a time duration much less than tau. So for example, tau is 1 second as an extreme case, but we are observing this waveform for only 1 millisecond. So the observation window, the observation time, this t, so from 0 to some t, is much less than the time constant. In other words, we are not interested in what happens later. We are only interested in the first, let's say, millisecond, while tau is 10 milliseconds, 100 milliseconds, 1 second, very large. Okay, so if t, the observation window from here to here, is much less than tau, I can approximate this exponential. You remember, exponential of a very small number is 1 plus that small number. So we can say that if t is much less than tau, then V1 x of minus t over tau is approximately equal to V1 1 minus t over tau. And this is not that surprising. The idea here is that if we are interested in only a very small part of this waveform, we can approximate it by a straight line. This is a straight line, so we can approximate it by a straight line. Right? That's what all this says. Okay, good. So in the half-wave rectifier with a capacitor and a resistor connected to the output, if the decay is slow, we can approximate the decay by this waveform. So let's go back there for a second and see what we have seen so far. So what I'm saying is that this decay from here to here, which is in this simple circuit, a capacitor discharging through a resistor because the diode is off, can be approximated by a straight line going down. And that line is given by the initial voltage, whatever we have here, which we know. The voltage we have here is V0 minus VD on, peak minus one diode drop, multiplied by 1 minus T over tau, assuming that this is a very slow decay. The observation time for us is from here to here, approximately t in seconds. The time constant of this discharge is very large, much greater than our observation window. So we can approximate this line, this waveform here, by a straight decay, by a linear decay. So I will just remember that this voltage, the initial voltage, is equal to V0 minus VD out, VD on. So let's go back here and write for the half wave rectifier, we have V out is equal to V0 minus VD on multiplied by 1 minus T over tau. This is the decay behavior during the time the diode is off. Okay, so we approximated that exponential decay by a linear decay. Now what we are really interested in is the amount of decay at the end of that discharge. So we go back here, we are interested in this voltage here. We decayed and decayed and decayed until the diode turned on. So at this point, past this point, we don't decay anymore. So how much is the voltage here if we know the voltage here? So this voltage is V0 minus VD on. We are interested in this voltage. Now, we know the time from here to here. We said that's approximately equal to T in. We said if the ripple is small, then we can say the decay lasts about T in seconds. So we go back here and we replace T with T in. So we say V out at T equals T in is equal to V0 minus VD on 1 minus T in over tau, and this is an approximation. All right, so this is what we have. We had this decay. Remember, we charged up and then we decayed, and what we have found is the equation for this decay from here, which I'm assuming 0, to here, which I'm assuming approximately T in as a function of time. Okay, and that is the equation that we had, V out. All right, so what I'm really interested in is this height, how much we had at the beginning and how much we have after T in seconds. So we found the voltage at this point in time, that's this. We have the voltage at this time, which is just V0 minus VD on. If we subtract these two voltages, we find the amplitude of the ripple. So we say ripple amplitude is equal to V out at time equals 0 minus V out at time equals T in. So here we have V0 minus VD on. Here we have all of this. So the difference between these two is just that. So that's equal to V0 minus VD on times T in over tau. This is the ripple amplitude. Okay, tau is the time constant of the circuit, equal to R1C1. T in is the period of the input. Sometimes we prefer to express it as 1 over F in being the frequency of the input. So sometimes we write this as V0 minus VD on divided by divided by R1 C1 F in. F in is the input frequency. 60 hertz in US, 50 hertz in other countries for the line voltage. So this is a simple compact equation for the amplitude of ripple that we get here. We can see that if C1 is smaller and smaller, the ripple becomes larger and larger. Why? Well, it makes sense, because if the capacitor is small, the decay is really fast, faster and faster. So the ripple becomes larger. We are here, we decay down here. Of course, so long as the approximation of slow decay holds, this equation also holds. This equation also says that if R1 is small, the ripple is large. Why? Well, if R1 is small, again, the decay is faster. And that means that if we connect a heavier load, by heavy we mean a load that draws a lot of current, then the ripple will be larger. So if the charger, like this charger, drives a, let's say, a simple Bluetooth device, which doesn't draw much current, then ripple might be only 10 millivolts. But if the same charger has to drive something with a lot more current, let's say a laptop or some other device, then the ripple will be larger. And that's what this equation tells us. Okay, so it's a nice little equation that is very useful in trying to decide the values that we need here. This is usually given, but at least these two values, for a certain amount of ripple at the output of the half-wave rectifier. All right. Well, looks like we did not get a chance to look at the full-wave rectifier. And at this point, our time is up. So I will see you next time when we talk about the full-wave rectifier and we repeat all of these analyses for it. I will see you next time.